Thank you. I think when I started coming to AGUs, this many people at an Arctic session would have we wouldn't have believed this could happen. So the importance of the Arctic in the world has never been clearer. And so to be able to do this, and thanks so much to the organizers. Thank you for coming. I know it's late. I know there was beer around, but we'll go ahead and see what we can do here. I have some musk oxen there. We're going to use these musk oxen, so I will make the signs go away. And then we're going to focus in on the big fella there. And we're going to use him. I'm going to do just a little background. Okay? So we should do the fundamentals first. And I'm going to tell people I'm going to do this kind of thing everywhere all the time until you quit asking me, because I think it's really important. We are a huge geophysical force now. And, you know, the numbers, if CO2 could be seen easily rather than drifting away that we can't see it, a typical car makes a pound of CO2 per mile. If you took that and you compressed it to the density of water or the density of muskox ploppies or something like that, we would cover every road in America an inch deep every year. In 10 years, there would be no joggers in America. We would all be cross-country skiers. And the numbers are flabbergasting. In the United States, we throw away less than 1,000 pounds of stuff that goes to the dump in trash cans. We put almost 40,000 pounds per person per year of CO2 in the atmosphere, 40,000. And I don't think that's something that everyone in the U.S. is completely proud of, but that is the facts, okay? And that plus, and this is something I pulled out of some TV shows that we made a little while ago, we have known this, and you all know this. I'm preaching to the choir here, but we've known this for over a century, and the physics were especially worked out in the Hanscom Air Force Base by good physicists who were worrying about things like, how can you see the hot exhaust of an enemy bomber? And if you put the wrong sensor on a heat-seeking missile, it cannot see through the CO2. And this plus the fact that there is more heat coming up from the sun-warmed Earth than going down from enemy bombers is all you need to know. And so this basic thing, you can see the figure here. This is a satellite picture of the Earth cooling off to get rid of the heat from the sun-warmed Earth. And you also can see that CO2 blocks that. And if there were more CO2, it would block more of it. And, you know, that's basically the story. That and 40,000 pounds per person per year is basically the story. We could do this. And if you spent through all the talks here and a couple of other meetings, you would come up with this as the fundamental answer, which is if we use this knowledge, we end up with a bigger economy, we end up with more jobs, we end up with greater national security, we end up with a cleaner environment, and we end up screwing over fewer other people. And that's solid. There is a social cost of carbon, and if that's not reflected, you're hurting the economy. And if you don't like being nice to people and you want to scare them instead, preventing the Air Force doesn't understand heat-seeking missiles and scientists and satellites are liars gives you a smaller economy with fewer jobs, less national security, a dirtier environment in which we hurt other people. And that, you know, we're not going to spend much time on that at this meeting because there's a lot of other things down the road. But if you put all the pieces together, that is what we end up with. Using knowledge makes us better off. Pretending that there isn't knowledge makes us worse off. Okay. Now, if you were an economist, you say we should use that knowledge. But people who became coal miners did so honestly. And you're going to let them retire as coal miners, and their kids will do something else. People who invested in coal plants are going to get their money back, and then their kids will invest in something else. You spend 30, 40, 50 years making the change. Do we have that? And the answer may depend on an analogy I want to draw for you. It may depend on dragons. So if you haven't seen this, this is a wonderful artifact. This is the Hunt Lennox globe. It's a little copper sphere about 4 inches in diameter. It's held together by tension with a wire through the poles. it is probably the second oldest known globe that shows the Americas. It was discovered in an antiquities mart in Paris in the 1800s. We're not sure where it was between its founding and then, but up there it says circa 1510. It may have been 1504, and it may be a copy of the oldest globe, which was put on an ostrich egg, oddly enough. Making globes has not always been as easy, and an ostrich egg was a little easier. Now, here's a picture of it in color. I swiped these from the web, but this is the Americas. So you're looking at South America there, and if we take the Wikimedia version of it and we zoom in, there's South America. And South America looks about right. And here is North America, and it doesn't. Okay? The three little islands. Columbus showed the map makers what they didn't know. And they didn't know what to put out there for a while. And way over here on the other side, if you zoom in, and you zoom in, and you translate the Latin, it says, "Here be dragons." And if you've ever seen "Here be dragons," this is where it came from. This is the first known use of this. It may refer to Komodo dragons over there in Asia, but it may refer to what we don't know. Because Columbus did show us what we don't know. This is often the story of exploration. We get something rubs our nose in it that we are ignorant. And what's possible? It could be islands, it could be a continent, there could be weird things swimming around it, maybe there are dragons there. You do more study and you cut off the dragon's tail, or in rare cases you find the dragon. Right? And this is a fantastic communications challenge. Because if you come out and tell people that there might possibly be dragons there, and then later you don't find any, they say, "Oh, you scientists are always being alarmists, so you'll get bigger grants." Those same people, if you didn't warn them of the possibility of dragons and somebody got eaten, would be really mad. And so this is something we always run into, and I'm not sure we'll ever get past it, to be perfectly honest. At any rate, I had the remarkable honor of helping the National Research Council, the National Academy, 2002, put out a report on abrupt climate change. And there is a session going on that's looking at the update of that report, which is over on the right, Abrupt Impacts of Climate Change, Anticipating Surprises. This is really about the dragons, and you will actually see hidden right under there the Hunt Lennox globe. So it's in there. And let's talk a little about some possible dragons. This is a figure from that new report, and the atmosphere has this much carbon in it, in round numbers. And the soils of the Arctic have that much in it. And the frozen clathrates of the seafloor, heaven knows how much is down there, but it could be a huge amount. And compare those to what we think is in fossil fuels, and these are huge numbers. Just huge numbers. Arctic soils are fantastically important. Methane hydrates can be fantastically important. Now, you know the story, a lot of you, for the seafloor especially, when it became evident that down in the sediments there were these solid clathrate ices and there was this free gas underneath, any sane and reasonable scientist would ask, could the free gas come out in a hurry? And we didn't really know. And so when you put the whole uncertainty distribution in, you had to leave at least a very slight chance of giant methane belches changing the world. And you know the answer, which is no, we do not believe we will have giant methane belches that change the world. And why? Because we have discovered the safety valves. If you want more free gas below the hydrate layer, you need higher pressure to push water out of the way. Higher pressure can open a crack through the hydrate layer and let it bubble out. In addition, when you freeze the salty water to make clathrate hydrate, it rejects salt. And that depresses the melting point, and you can get free, very salty water existing that can allow methane to bubble through the hydrate layer. And so because we have safety valves, it's hard to get enough free gas to really change the whole world hiding beneath that hydrate layer. Then, to break it down, it's a heat conduction problem. And heat conduction always has longer time scales. And so this is something that matters hugely for the future. But it's something that is not likely to happen like that. It's not likely to be a dragon just because there really are safety valves. The same probably applies to that permafrost carbon. If you want to turn all of that frozen stuff into methane, it takes a lot of bugs. And bugs have ecosystems, and they worry about wet or dry and frozen or not frozen. And getting all of them to do the same thing at the same time fast enough to make giant methane belches is really hard. You still worry a little bit about what fire could do to some of them, but overall, you look at these and say, look, they will matter for our future. Understanding these is greatly important, but they don't seem like they're something that's going to produce giant methane belches fast enough to really be a dragon. And so we should know. Knowledge of this is important, it's valuable, it must inform projections of the future, but it's not a dragon that's going to eat you. Maybe it's, I know there's a debate in the public realm whether zombies are fast or slow, but if you want to think of this as a zombie that comes after you slowly, but inexorably, maybe that's more accurate. Okay. I want to do something else because I think this is important, and I'll come back to it at the end. I just said, look, no methane belches. How sure am I of that? Okay? And the story I'll tell you, and I think this is relevant to how sure are we? How sure should the scientific community be? Should we tell the public this is impossible? Okay, so at any rate, back in my grad student days, I went to Antarctica, I took a sediment core, it melted on the way home, or I took an ice core, it melted on the way home. I had to get some more ice for my dissertation. I went to Greenland, I went back to Antarctica, and the Air Wing commander found me in Antarctica, and he said, I'm going to Greenland, we're going to do GISP 2. And he says, you were up there near there, am I going to fall in a crevasse? And I explained it to him in great length, all the glaciology of why I was confident that he would not fall in a crevasse. Okay, this and that, and the remote sensing, and the flow state, and all these other things. I gave him the full glaciology that only a grad student who's trying to sound like he knows what he's doing can do. Okay, and I know a lot of our graduate students know what they're doing. I was trying. Okay, at any rate, he then said, in basically these words, I have to admit that I wasn't writing them down. He said basically in these words, he said, if I fall in a crevasse, I'm going to come back and find you. I'm going to put your reproductive organs in a vise. I'm going to set the table on fire, and I'm going to give you a butcher knife. Are you sure? Okay, this puts it really in a different context. Right, and you know what I said is he'd take out insurance. And some of you who have been to the Antarctic know this, or the Greenland. You fly the plane while dragging the skis, and if there's a snow bridge over a crevasse, it'll break it. You take off, come around, and you look before you put it down. It's called a ski drag, and of course he was going to do that anyway. He knew what he was doing. But at any rate, you get into this, are you sure? No. Okay, people who demand perfect foresight are not living in the real world, and that really does have implications for how we view abrupt climate change that we will come back to. But first of all, I want to walk you through an update of what we learned when the airlift commander landed in Greenland, and no, he did not fall in a crevasse. I was right. Okay, so at any rate, many of you know this story very, very well. This is time on the bottom. Today is over on your left. 10,000 years ago is over on your right. Here is the broad arch of the history of temperature in Greenland, not the world, but in Greenland, that is linked to features of Earth's orbit. The wiggles are linked to sun and volcanoes and probably ocean circulation and maybe some other things, and one big flood right there. These wiggles have names often because they were big enough to matter to people, and so they named them. And of course, you know what I'm doing to you. I'm leaving this big void over here on the right, and that is climate change. And if these wiggles are big enough to matter to people, that sucker is interesting. And it is about 10 Celsius in about 10 years in Greenland. It's, you know, I mean, they're big. And it's real. And it shows up in lots of cores. It shows up in lots of indicators. Those temperatures really are good. If we, the previous slide is over there on the left and very faded, so the previous slide was here, and this happened a lot of times. This is not a one-off. This is a feature of the climate system that ran through the Ice Age and through previous Ice Ages. There were some sessions on that here at AGU this time, but through previous Ice Ages as well. And it's at least interesting that agriculture shows up all over the world as soon as this craziness stopped. People, a few million people probably had filled the world, and they settled down with their diseases and their gruel to raise a little extra food for their kids about the time when it looks like it became possible. I will not insist on that. Boy, you start into this subject very far and you will find lots of discussion, but it's interesting at least. Okay. The next slide, we're going to zoom in on that little blue band that I just popped in right here. And we will get something that's very important from the Ice Ages. So the previous one is now this blue-purple thing in the middle. This is temperature. And I have squashed it down enough that it doesn't look very alarming. I've got accumulation just above it there, but then I've got a couple of plots below it. This is methane coming from the high-latitude wetlands and coming from the tropical wetlands. This is dust. It has the isotopic and chemical signature of Asia. This is not just a story about Greenland or the Arctic. This is a story about the world coming out of the Arctic. The one on top I'm going to blow up in a different color on the next slide. Greenland is now in green, and Venezuela is in red from Huygens et al. And this is ultimately just the color of a sediment core off the coast of Venezuela, but ultimately this is the position of the intertropical convergence zone. And when Greenland was cold, dry, and windy, the intertropical convergence zone had fled southward, and off the coast of Venezuela at the Cariaco Basin was also cold, dry, and windy. It is not just a story about Greenland and the Arctic, it's a story about the world. You can, Larry Edwards' work, there's lots of new versions of this figure that are prettier, but the basic pattern we knew from the methane and from the interhemispheric gradient that the tropics were involved. You go to cave formations recording water in the monsoon belt, and you find the tropics were involved, and the monsoon belt is playing, and every event in Greenland has a corresponding event in the monsoon belt. It's also in Antarctica. There's lots of new versions of this figure too. 10,000 years ago was over here on your left, 90,000 years ago was over on your right, Greenland in green, Antarctica in red, the broad cycle of the Ice Age in both. North and South have the same Ice Age, despite having somewhat different sun because of the effects of CO2, and riding on the back of it are all these abrupt things. And if I take a little digital filter and I get rid of the Ice Age, you can see that our cold in Greenland goes with warm in Antarctica, and our warm in Greenland goes to cold in Antarctica. And back here you see green is up and red is down, and red is up and green is down, and green is up and red is down, and very clearly every event in the north is in the south, as well as being in the monsoon belt, as well as being in Asian dust and what have you. That is ultimately the anomaly pattern, or a pretty good picture of the anomaly pattern that Bill Curry made up for me a few years ago, is when you make it cold, dry, and windy up in Greenland, the whole world doesn't change its temperature very much, but everybody on the world would have noticed a different climate, winds or rain or something. This rearranges the planet's weather coming out of the high latitudes of the north. Why? This is, you know, Oceanography 101. You all know this, but in case you want this someday for your students, they can watch this, and you can sit down for a minute in class. This is the Levitas Atlas, and what you see here is temperature in the surface ocean. And what you will notice is when you get near the pole in the south, all of the water is cold. When you get near the pole in the north, all of the water is cold except off of Norway where it's warm. The only warm water that gets near a pole anywhere in the world ocean is right up here. There it is, only warm water near a pole. Okay, this is the salinity. And you know why this is. As you get towards the pole in the south, green is low salinity. The water is relatively fresh. The atmosphere is raining on it or snowing on it. As you go in the north, it's very fresh in the restrained Arctic basin, except for this little plume of salty water, which is coming up here where the warmth was. And you'll also notice very clearly the Atlantic is salty and the Pacific is relatively fresh. And that is fundamentally, it's a little more complicated than this, but fundamentally it is because water evaporates from the Caribbean and it blows in the trade winds across Panama, but it can't get back. Can't get back because Panama is in the way. And so now you get into this problem that somehow we got to get the salty water here back to the fresh over here before this turns into a salt pan and this turns into a giant swimming pool. And you know Wally Broker has done this for a lot of decades now, it's a Rube Goldberg device. The water goes up here, it sinks, it goes south, it goes around and round and round, it comes up under here, it mixes up to the surface, and eventually you get the salt and the fresh water back together again. But the accident of Panama, this particular picture actually has a sea level canal there. It shouldn't, but if this picture were right, Wally's conveyor would probably go away. Okay, so what happened in those abrupt climate changes? When you cool seawater in the winter, it contracts. If it is slightly saltier than the average ocean, it can sink before it freezes. If it is slightly fresher than the average ocean, it freezes before it sinks. Today, off of Norway in winter, the water sinks. It's replaced by warmer water, which comes from the south, and the British play football all winter. If you make it fresher off of Norway, you freeze in the winter. That cools the winter. It doesn't do too much in the summer. It's offset by warming in the south, and the British would compete with Canada in hockey. So basically, there's what was happening. But the trade winds still blow across blow Atlantic evaporation to Panama to rain on the Pacific. And so you can't, if you stop the sinking in the north, you get into a problem, because you're losing fresh water from the Atlantic basin. Eventually it's going to restart. When it restarts, it will be really salty and it will sink really well, and you will get a really abrupt change, and that will be a tipping point. That, again, to remind you, is the anomaly pattern. If you simulate it, there's probably hundreds of simulations and hundreds of papers that have looked at this, and they basically do it. So this is Valinga and Wood from O2, Journal of Climate, and what you see is when you freshen the North Atlantic, the north gets cold, the south gets warm, the north gets dry, the intertropical convergence zone kicks south, the monsoons get kicked a little bit off of Asia, so you get wetting and drying and big changes where a lot of billions of people now live. Okay. Not another ice age, but it did matter. It also probably played a big role in the Ice Age CO2 story, because when you force the circulation south, it puts the winds in the Drake Passage that move lots of water that allow CO2 to come out of the ocean. So it may have been indirectly very important in global temperature, but not directly important in global temperature. It's mostly just a seesaw, but it did probably change the climate for almost everyone. Okay? If anyone saw the movie, It's wonderful science fiction. I enjoyed it, but, you know, yeah. Okay, so that should do it. Okay, but even though we are fairly confident, based on good modeling, that we will not freshen the North Atlantic fast enough to shut it down in a hurry, we are fairly confident that we will freshen the North Atlantic and that that will change the strength of the circulation. We're not 100%. If the commander came after me with his vice and his butcher knife, I'd still give him a chance that something could happen up there. But you may have possibly seen this paper from Ferguson et al. That just came out in Nature Geoscience that notes that we likely do change the strength of the overturning circulation in the future, warming, freshening, and slowing. And that if that changes, precipitation patterns in the tropics are likely to respond. And where there's these really steep gradients between really wet and really dry, moving them is going to put somebody in a wetter place and somebody else in a drier place, and there's some danger that there's a national boundary between those two. And they can't just chase the rains without going over a boundary where somebody may have guns and not like them. And so even though we don't think we're going to get any younger Dryas out of this, it really might be another slow zombie. It's not a fast dragon with fairly high confidence, but this is likely to matter. It's a place that plays in the global picture. Okay? It also reminds us so much of the change was linked to sea ice. And it reminds us what a remarkably powerful lever sea ice is. The difference between open water in a dark Arctic winter and sea ice can be 40 degrees. And so you start looking at this and you say, wow, this is something that has got to matter. And you know what sea ice is doing, so I swiped this one from the IPCC website, from the new report, not quite yet finalized, but 1860 is over on your left. Here's sea ice, and you notice what sea ice extent is doing. This is the minimum of the year, and lots of different ways to measure it, and you get the same answer, that sea ice has been shrinking a lot in a big hurry. And we sort of all knew that. Polyak et al., the review paper came out of the CCSP. The current reduction started in the late 19th century, consistent with warming. The ice loss appears to be unmatched over at least the last few thousand years, unexplainable by any known natural variabilities. Warming is reducing the sea ice. Okay. You've probably seen some of this. I am confident that we are going to see more of it. This is an exciting, a fascinating area of research. I don't think it's done, but it's worth keeping track of. In the past, when Arctic sea ice changed, the world knew it. Arctic sea ice is changing. And there is some literature, including this brand new one from Nature Climate Change, pointing out that more frequent extreme summer heat events over mid-latitude continents are linked to reduced sea ice and snow through circulation changes. And if you saw Sewell and Sloan, Lisa Sloan here, 2004, disappearing Arctic sea ice reduces available water in the American West. Okay. It isn't clear from any of these that the linkages are quite as strong as they were during the Younger Dryas, but it's fairly clear that the Arctic can't just go its own way with the rest of the world ignoring it. And just how strong these linkages are, how fast, what they explain, like I say, I think this will be one of the most fascinating things. It's one that a lot of research is going to have to happen on. But it's pretty clear that the Arctic is going to end up still mattering far beyond the Arctic. Now, there's an additional complication that I'll mention briefly, that some of those big jumps in the North Atlantic during the Ice Age were associated with what we call Heinrich events. And if you go out in the ocean, I think I've got a picture here. If you go out in the ocean and take a sediment core, you find layers of shells of small dead bugs. And then you find layers of pieces of the Hudson Bay. And then dead bugs in Hudson Bay, and dead bugs in Hudson Bay, and dead bugs in Hudson Bay. And the Hudson Bay is called Heinrich layers. And we're pretty sure that they're telling us this story. An ice sheet flows down to the ocean. It doesn't always immediately break off. It can flow over the ocean while attached as an ice shelf. Ice shelves serve a couple of roles. One of them is they keep the iceberg attached to the ice sheet until the bottom can melt and the rocks fall out. So an ice shelf is a filter to keep from having rocks in your icebergs. Ice shelves also have friction with the bay sides and with local high spots in the bed, and so they hold back the ice that's behind them. So when you have an ice shelf in front of your ice sheet is big and slow, and your icebergs are clean. If you warm it up, the ice shelf breaks off, and then your ice sheet goes fast and gets thin, and it puts out lots of icebergs with rocks in them. And so our understanding is that what you're looking at is, at times, maybe subsurface warming at the grounding line, some work of Peter Clark, indicates that the ice shelves broke off in the north, and then that caused fast flow, which would contribute to sea level rise, and it caused layers of Hudson Strait rocks to show up out in the middle of the Atlantic. Okay? This could matter in our future. There's a lot of ice on Greenland. There's a lot more ice on Antarctica. And this tells us that these changes really did happen in the past. And you can see it very clearly in the sediment record. Okay? Jakobshavn in Greenland, 1 degree ocean warming thinned the ice shelf, which then broke off. And the flow speed almost tripled. And dirty icebergs started showing up in the fjord, the kind of thing that would make a Heinrich event. And Jakobshavn can't evacuate all of Greenland because Greenland's got a shallow bed in the middle. There are glaciers in Antarctica that could evacuate a lot more ice. And so this is a real issue that we might actually have a hold of the tail of a real dragon and not just a zombie on this one. Okay, this is a picture of Jakobshavn. Ian Jochen gave me this, and the ice sheet is over here, broken up icebergs in ocean water down to your left, and you can see the dirty icebergs that could contribute to a Heinrich layer if they were out at the fjord mouth. Okay. I'm going to walk you through one more little story, and then we'll close her off here with some summary. Time is really different here. First of all, I've turned it around backwards, so today is over on your right rather than your left. And the 400 here is now 400 million years, so we're looking deep time. And what you see on this is two things. One is an estimate of CO2 from various indicators. This is ultimately from the IPCC, from other sources. The other one is the indication of how far the ice came. And so you can see the ice extending way towards the equator recently when CO2 is low. High CO2, no ice at sea level, even in the Arctic. Low CO2, ice. There's actually a little drop in CO2 that goes with this one pretty clearly. And we're going to focus in on this one right here. So if we go forward, the dinosaurs are killed by the meteorite just off the left end of this. And you can see a broad change in temperature, which is more or less driven by a broad change in CO2 with little wiggles. The growth of ice in the south and in the north. And then this little blip right here. It was pretty warm. And then it got warmer. And the indications probably are looking at summer temperatures, but I have this in Fahrenheit and I think on the next plot in Celsius, but indications are warming in the Arctic of about 9 Fahrenheit and 14 on land, and temperatures up in the mid-70s in the summer out in the ocean. Pretty warm thing there. I will show you a couple of figures that walk through this, but let me first of all sort of run through the effects for you briefly. This was CO2. It may have come out as methane first, but it was ultimately CO2. The world warmed, the Arctic warmed more. If models have a problem, it's that the warming looks a little bigger than models like, not a little smaller. It acidified the ocean. There's a seafloor extinction event. It did lots of other things. It changed where plants and animals lived. It changed the animals. It changed pretty much everything you can get your hands on. It shows that CO2 warms. The recovery time scale is about right. And it's clearly a CO2 thing, not a drifted continents thing. You can see it, so I swiped this picture from Zakos et al. In Science. It's a fantastic paper. The lighter colors here are small dead bug shells, carbonate. The darker color is the carbonate is gone because it was dissolved because the ocean was so acidic that it was eating up its sediments. This one coming forward in time from 56 million to 54 million years, 56 on your left. Drop here is a rise in CO2 from formerly living things, so there is the CO2 spike, this is temperature, and there is the temperature spike. And it's hard to miss this one. It's very clear. This one from Carano et al. Is swiped from PNAS. Peter Wolf, my colleague, is involved in this research, and you find the fossil leaves are chomped on. Look at all these glorious pictures of insects eating leaves. It's sort of, there's more of it in this interval than before or after, which suggests invasive species, it suggests ecosystem disruptions, it suggests a lot of things that are shown here in mute testimony. And then this one is slightly complicated. It came out in Science in 2012. Over here on the left, these are various critters. Stars mean no data, and everything else says it got small in the PETM. When the temperature went up, the body size went down, and then afterwards everything got big again. And you sit there and you say, so what would make critters get small? And surface to volume ratio comes to mind. Big critters have troubles losing heat, and they couldn't compete with the little critters. A world where it's hot enough that everything is trying to shrink because it's hot is what this looks like. That's what the literature is pointing at. I wouldn't tell the commander absolutely positive yet, but that's what it looks like, is it got too hot for big critters. Okay. So what do we say about Arctic abrupt change? It's probably the easiest place to see the changes. They can be huge, they can be fast, they can be disruptive, they can kick the world. A lot of things that we care about, a lot of native lifestyles, a lot of unique, rare, and endangered species are certainly on the line in a warming Arctic. But from a purely economic standpoint, there are shipping companies and mineral companies and oil companies that are just waiting for that ice to shrink because there will be economics up there. And so for the warming in the Arctic, while it loses much, it opens other opportunities. The warming might be more worrisome in places where it's already a little hot to live or to grow crops or otherwise. And of course, you remember that the world is this big Arctic, or this big equatorial band and this little Arctic cap. And the big part, a lot of it, is a little uncomfortable for people without air conditioning already. This one also showed up in Science this summer. There's been a lot of people looked at how does climate change affect how we get along with our neighbors. And this study did an overview of a whole lot of studies, and each of these panels in the middle is 0, and to the left is climate cooling, and to the right is climate warming, with 1 degree that much there. And then these are changes in risk of conflict of various types. And basically what you find when people expect a climate, and when they don't get it, it almost always is costly to them. And if it's costly to them, they may get unhappy and they may not have enough food, and it seems like they get unhappy with their neighbors. But the hot side, at least in these cases, looks like it's worse than the cold side. And so and the changes so far are very small compared to what we could do. We can head back towards PETM levels if we burn it all. Right? So let me do this. I have showed this in many places, many times. I intend to do it again. I get to ride my bicycle, but if you're a commuter, you know the story, which is the most likely thing that happens to a commuter is you get stuck in traffic for a while. And you turn on the radio and it's no fun. The best thing a commuter can hope for is no traffic in the Beach Boys Festival. You might get stuck in really bad traffic and you get the test of the emergency broadcast system and you might get run over by a drunk driver. Now, what do we do about this? We spend a lot of money. And we get automobile engineers to design airbags and crumple zones and anti-lock brakes and seat belts and child seats for the kids. And we donate to Mothers Against Drunk Driving, and we pay to train bartenders to recognize drunks, and we pay police to get out there and protect us. We pay traffic engineers to make the roads safer. We put a lot of money into something we don't actually expect to happen, because if it does, it's so terrible. And when you look at what we face from the CO2 that we are putting up, and that is having a warming influence based on physics that we can't avoid, there's a best estimate, and it's real science. And real science means that there are uncertainties on both sides, and we may be overestimating the danger. It may be better than that. But, you know, we're not expecting and it's real science. And real science means that there are uncertainties on both sides. And we may be overestimating the danger. It may be better than that. But, you know, we're not expecting the ice sheet to collapse. We're not expecting to lose the Amazonian rainforest. We're not expecting all that carbon and frozen in soils in the Arctic to come out fast, or frozen in the seafloor to come out fast. There is some chance hanging out here of reasonably bad things. And we know if you want to build a building, you can't do it with just a hammer. It takes getting a lot of things right to build something. But you can break a building with a wrecking ball or a stick of dynamite. Breaking is way the heck easier than building. And that, just cranking up CO2 doesn't make Eden, because that means getting a lot of things right. You don't just move your crops from Kansas to Greenland or central Ontario when it gets warmer, because day and night are different and lots of things are different, and it just happens that the soil of central Ontario is growing crops down in Iowa. And this doesn't work really well. And so CO2 doesn't seem like it would make Eden, but it does seem like it could cause really big damaging things that would make a huge difference. And the mere fact that CO2 is a greenhouse gas, we're emitting a lot of it, we're swinging a hammer. And the less you trust the science, you know, there might be things out there. I can tell you that I have indeed spent a fair amount of my life having this argument in places like congressional hearings. Here's our best estimate, couldn't it be better? Here's our best estimate, couldn't it be better? Here's our best estimate, I'll bet it's better. Look, we just heard both sides. Okay? It would be more accurate to have an IPCCer argue with an environmentalist than it would to argue with a don't worry, be happier, because of the distribution of the uncertainties. Okay? So let me finish. I believe I get to teach, It's fantastic, and we have a lot of bright students who want to make a big difference, and I believe that they are going to invent things, they are going to learn things, they are going to give us more knowledge, building on what we already have, which shows very clearly that if what we know is used in a wise way, it makes people better off. And if what we use is used in a wise way, we can get along with each other better, and we really can avoid dragons that really might be out there. Thank you for coming. Thank you for inviting me.
Thank you.
Oh, absolutely, please. Use that one, I'll use this one. Okay.
Okay, many thanks to Richard. We have a few moments for questions. Please stick your hand up and stand up, and
there is a mic down front here, so either
Yes,
yell or
yes.
come down front, or if you're close to the
best
front,
if
I'll
you
bring
can-
you one.
Mike.
Yeah, here
Yes,
we go.
come on towards the mic. Well, the mountain is coming to Mohammed, or vice versa.
I think that was a wonderful presentation that brought up a lot of issues, but that are very important for scientists to think about. My concern is that I think there are precisely 0 examples in history where a society has dealt with low probability, or even where low might be, you know, lower than 80%, and distant future, meaning more than about 15 years, problems. And so I think that's an important response to those concerns. I realize that you were brought here to talk about a specific issue, and so how do we as scientists think about the real world of how political decisions are made in that context?
Right. So if you take the IPCC numbers and you say, okay, what is the best thing to do about those? The answer is we do a little bit to slow down climate change, but not a lot. But if you take the recent report from the IMF and the recent report from the EIA, right now, world government policy in most places is serving to greatly accelerate climate change, because the IMF and the EIA say we are subsidizing fossil fuels much more than we are subsidizing renewables. So if you ignore the dragons, ignore the long tail, ignore the scary things, and just look at the central one, changes in policies would lead to economically better outcomes, stronger economy, more jobs, and so on. Then if you say, but we want to try to head off the dragons, you do more sooner. But just the basic economics of the thing says you end up better off if you quit subsidizing climate change. Now, be very clear. What is a subsidy is very different to different people. And I can tell you that there's a lot of folks would criticize the IMF and the EIA reports, but they indicate that we are now working very hard to speed up climate change.
Okay, gentleman in the center at the mic.
Thank you. Thank you. Quick response to the last question. There are not 0 examples. It's a set of measure 0, but there are not 0 examples. There's a really good book by Jared Diamond called Collapse: Why Societies Choose to Fail or Succeed. And it's a long litany of the usual disaster areas such as the Easter Island. But there are 2 or 3 examples that Diamond gives of societies that for who knows what reason actually figured it out and turned themselves around. I mean, a classic example is Tokugawa, Japan in the mid-1600s. On the verge of deforesting their whole island, they figured out that, oh, perhaps we should stop cutting down quite so many trees, and we should, take care of the soil and replant. And they actually did it. They had a clear long-term vision. And the other extraordinary example is the tiny island of Tikopia, sort of a counterexample, the Easter Island, a little island way off in the western Pacific, maintained a stable population of about 1,400 people for approximately 3,000 years. And rather unusual. I mean, I didn't know about that until I read Diamond's book. So, yeah, the statistics are not great on societies learning to correct themselves, but there are a few encouraging precedents. And well, of course, as a teacher, my assumption is that people can learn, so I keep trying. But
Yes. Point is very well taken. I also enjoyed reading that book. If you have not read it, it's not in your recent bookstore. It's called Collapse. And it was highly instructive for a lot of us, I believe. We certainly have done very much bigger things than what is needed. The estimates are 1% of the world economy per year would make a sustainable energy system. We've spent a lot more than that in what we used to call world wars. We spent about that much cleaning up sewer and water. So it's certainly well within the range of things that we have done. But it's probably a little bigger than anything we sat down, shook hands, and agreed to do.
Yeah, more questions.
Yes, way in the back.
Okay, he's better. Eyesight's better than mine, that's for sure.
Hang on.
Let's hang on till you get the mic, please.
Hello. In the Jared Diamond book, which is very instructive, he talks about how perhaps one might not perceive it when you are in the process of collapsing. And this is a very disturbing thought, which has worried me considerably. And it's a very frightening thought, because we've ticked all the boxes. If you look at the things that can lead to the collapse of a civilization, we tick all the boxes.
But if you look at all the things that could save a civilization, we got them too. And while things have collapsed over and over again, averaged across all people and the whole world, there's more of us living better than we ever did before. And the tools are there, and we know what they look like.
Okay, listen, many thanks to Richard. We're effectively out of time. I'd like you to join me in thanking him. I'll never think about zombies and dragons in the same way again. Thank you.
Thank you.
Oh, thank you.